Welcome to The Explainer. We're going to tackle a question that pretty much haunts every single aspiring developer out there. Why are tech companies so obsessed with data structures and algorithms? We're going to uncover the answer through a really simple story, the tale of two searches. And trust me, it reveals a multi-million-dollar secret behind the code you write every single day. Let's get right into it.
So, picture this. You're building awesome projects, you know your favorite programming language like the back of your hand, but then you hit the interview circuit. And it just feels like every company, from the huge giants down to the tiny startups, they're all hitting you with these tricky DSA questions. I hear it all the time. What's the big deal? Why this obsession? Well, it all boils down to one simple and very expensive truth.
And this quote, it gets right to the heart of it. See, every single time you scroll through Instagram or search for something or really do anything online, you're running code on a server somewhere. And guess what? Those computations are not free. Nope. Companies like Meta, they're paying cloud providers like Amazon for every little bit of processing power. Your code has a real-world cost. An inefficient code? Oh man, that can cost millions.
And that right there is where DSA comes into play. It's not just about solving some clever puzzles for an interview. At its core, it's all about one thing: efficiency. It's the whole science of organizing your data in a way that lets you do stuff, like searching or sorting, using the least amount of time and the least amount of memory possible. It's all about being smart with your resources. To really see what that means, let's look at a classic problem.
Okay, so let's start our story with the most obvious, most straightforward way to solve a problem. This is what we call the brute force method. It's simple, it's super intuitive, but as we're about to find out, it has a major hidden cost.
So here's our challenge. We've got a list of numbers, and it's already sorted from smallest to largest. It's a big list, 10,000 numbers, and somewhere in there is the number 900. Our job? Just write a program to find it. Sounds simple enough, right? Let's see how our first search method handles this.
This is linear search. And yeah, it does exactly what you'd think. It starts right at the beginning of the list and asks, hey, are you 900? Nope. Okay, how about you? Are you 900? Still no? Okay, next. It just kind of plods along, one by one, checking every single element until it either finds the number or it hits the very end of the list.
So what happens if our number, 900, is the very last item in the list? Or even worse, what if it's not in the list at all? Well, in that worst-case scenario, our simple linear search would have to make 10,000 checks, 10,000 steps, just to find one number. In the world of computing, that is incredibly slow and super expensive. There has to be a better way, right?
And of course there is. This is where just a little bit of algorithmic thinking can completely change the entire game. Instead of that brute force approach, we can use a really clever strategy, a trick known as divide and conquer.
So, let's introduce the hero of our story, binary search. Where linear search is simple but slow, binary search is elegant, it's clever, and it is blindingly fast. And it's all because it takes advantage of one key piece of information that linear search completely ignored: the fact that the list is already sorted.
Okay, here's the magic. Instead of starting at the beginning, binary search jumps straight to the middle of the list, and it just asks one question. Is the number I'm looking for, 900, bigger or smaller than this middle number? Now, because the list is sorted, if 900 is smaller, we know it can't possibly be in the entire second half of the list. So we just throw that half away, gone. In one single step, we've eliminated 5,000 possibilities. Then we just do it again on the half that's left. So, by repeatedly cutting the problem in half, how many steps does binary search take in the worst case? Is it 10,000? 1,000? 100? No, just 14. That's it. From 10,000 steps all the way down to 14. This is the power of a good algorithm, and this is the kind of mind-blowing efficiency that saves companies millions of dollars. Now, this massive difference isn't just some cool party trick. It's a fundamental concept in computer science, and we actually have a formal way to measure and talk about this incredible difference in efficiency between our two search methods.
It's called time complexity. And what's really important to get here is that we don't measure this in seconds. Why? Because a super fast computer might run a bad algorithm faster than a slow computer runs a good one. That's not a fair comparison. So instead, we count the number of operations, the number of steps. This lets us compare algorithms fairly and predict how they're going to perform as our data grows from 1,000 items to 1 million or even 1 billion.
And we use something called big O notation to talk about this.
So linear search is what we call O of n, which basically just means the number of steps grows directly in line with the number of items n. 10 times the data, 10 times the work. Simple. But binary search, that's O of log n. Now, what does that mean? Well, think of looking for a name in a phone book. You don't start at A and read every single name, right? You open in the middle, decide which half the name is in, and then you do it again. That's a logarithm, and that's why even when the data size explodes, the number of steps barely even budges. It grows incredibly slowly.
I mean, just look at this chart. It could not be clearer. On one side, you have this huge mountain of 10,000 steps for linear search, and on the other, that tiny little bump of 14 steps for binary search. This visual says it all, really. Choosing the right algorithm isn't just some small optimization. It's the difference between a system that actually works and one that just grinds to a complete halt.
So let's bring this all back home, back to you. Why do companies care so much about this stuff? Because honestly, understanding these concepts, it gives you a superpower as a developer.
Choosing the right data structure and the right algorithm can turn a problem that seems impossible into something trivial, and that saves real time and real money. Just remember, more steps always equals more cost. Of course, there are trade-offs. Our superhero binary search only works its magic if the data is sorted first. But the most important thing is this. Thinking this way fundamentally changes how you solve problems. It makes you a more effective, more efficient, and way more valuable programmer.
And that, at the end of the day, is the real reason tech companies are so obsessed with DSA. They're not just looking for people who can write code. They're looking for people who can think. People who don't just find a solution, but who can find the best solution. So the next time you sit down to build something, ask yourself this question. What's the easy, brute force way to do this, and what's the smarter way?